quarter of this looks like is we might talk about the Laplace transform, we might talk about Fourier transform, we might talk about what's called the Dirichlet problem, which is, the Dirichlet problem is like basically the solution to the heat equation on a ring, right? Like, which motivates a lot of where complex analysis came from originally. We'll talk about conformal maps. There'll be more work on, there might be some work on complex dynamics or complex geometry. They're just, once you get the foundations down, it can go a lot of different directions. All right. Okay, so today's a fun day because we're going to start with something easy, and then I'm going to prove that I'm going to prove a fact that probably you've never thought about before, because when you were taught it in calculus, you did it without thinking about it. So we're going to prove that it's okay, not only that it's okay to take the derivative of a power series term by term, but that when you do that, that the function you get out is the same as the function you get out of the difference quotient, which maybe you didn't realize was even possible, something that needed to be proved, but that's what we're going to do today. And in the course of doing that, what we're going to prove is the first half of sort of the central theorem of complex analysis, which is an analytic function, so that function with a power series, is automatically a holomorphic function, which means infinitely once and therefore infinitely differentiable. So we're going to show the analytic implies holomorphic direction of that today. And then the holomorphic implies analytic, we'll have to wait until we've got the Cauchy integral theorem, which is, 2 chapters ahead or something. So, okay, so where does the motivation for this originally come from? Since we're talking about this now because we're still talking about good old e to the z. So e to the z is going to motivate our conversation today. So, what is the power series for e to the z? I keep asking you, and I ask you again. What's e to the z equal to? Okay, that's one way to think about it. We're not going to use that. We're going to use the power series today. 1 plus z squared over 2 factorial, and so on, right? Okay, so e to the z is this power series. We're just going to accept that by the extension theorem that this power series holds for an infinite radius of convergence. So this function is entire. Okay, so the first thing that I'd like to argue here is that even though when you were taught Taylor series in calculus, whenever that was, one thing that we taught you how to do when we teach you Taylor series in calculus is, it's okay to take the derivative of a function by just taking the term-by-term derivative of the power series. As long as it converges, you're allowed to do that. So maybe you've done the thing where you said, since e to the z is equal to this, clearly d by dz of e to the z is equal to 0 plus 1 times z to the 0 plus 2 times z to the first over 2 factorial, and so on. But then all that cancels, and you end up with 1 plus, 2 over 2 factorial, the 2's cancel. I should put one more term in here. 3z squared over 3 factorial. And so when you take the derivative of the power series, after you do the cancellation, you end up with the same power series. The 2 hits the 2 and turns this into the z to the first over 1 factorial. The 3 hits the 3 and turns this into z squared over 3 factorial. And lo and behold, you get the same function out that you put in. Right? So the derivative of the power series of e is itself. Did I switch something around here? Oh, yeah. 2. Okay, so which is e to the z. However, we have not actually done what you think we did. We didn't do this. We did this. We show the derivative of the power series is equal to e to the z. D by dz of e to the z means something different. D by dz of e to the z means the limit as h goes to 0 of e to the z plus h minus e to the z over h. Why should it be the case that those are the same? I mean, we want them to be the same. If differentiation of power series works the way that we think it should be the case that if e to the z is equal to this power series, and I take the derivative of the power series, it converges and is equal to whatever the derivative of e to the z is. Just because a function is equal to a power series, nobody ever proved for you that the derivative of a function was equal to the derivative of its power series. We did it, and nobody proved it. And so that's one of the things we're going to work on today is that like this is a central idea. So this is somebody earlier pointed out that this class seems to go back and forth between like tame and easy and wild. Today is going to be kind of a wild day in the sense we're going to be proving something, but we're going to prove that. Yep.
Sorry, this doesn't apply necessarily to Fourier series, right?
Fourier series are a different issue because the convergence there has like
Right.
there's way more complications going on with Fourier series.
Okay.
We'll talk about that when we get to
I thought I
the
remembered that from my PE.
we will talk about like this is not a Fourier series.
Right.
Fourier series have terms that have negative powers in them. Is the thing, right? So we're not dealing with Fourier series at the moment. We will.
Yeah,
but
I
not
just
yet.
wanted to check that.
Yeah.
out.
Okay. So let's actually just for e to the z, let's actually check this. This is a good exercise. So first off, I hope it's like people see the difference. Like the point I'm trying to make here is that the derivative of the power series is e to the z. But why should it be the case that the derivative of the power series matches the derivative of the function? We want that to be the case. So what is this difference quotient? How do I proceed?
Can you substitute in the power series for both?
Well, it would be useful to do that if I did this first. Okay, now, there's a trap here. Because I'm hoping somebody gives me the wrong answer to this question. How do I deal with this limit right here? E to the h minus 1 over h. No, that's the right answer. Don't give me the right answer. Give me the wrong answers only. No, oh, okay, well, 0 over 0. 0 over 0, that should seem familiar. Oh, there's the wrong answer I was looking for. Okay, when you are, congratulations. When you're doing something like this in complex variables, I want you to be careful about the evaluation of limits, okay? So L'Hopital's rule is a theorem that is proved in real variable theory using derivatives, right? And the structure of real derivatives. You don't just get to assert, like this h here, remember these limits are not limits in the one variable sense. This is a limit in the sense of complex analysis. It's all values that are close to h simultaneously is what we're thinking about. So I can't use L'Hopital's rule. So the Taylor representation of e to the h, that's what we want to use, the power series for e to the h. So what is the power series for e to the h? How many terms do I actually need here is the question. 2. So I need the 1, and it would be nice if I had the h. And now I'm going to show you the physicist slash engineer slash applied mathematics trick, which is plus O of h squared. Okay, what do I mean by that? I mean, every other term is at least h squared. So h squared, h to the third, h to the fourth, h to the fifth. This is a measure of how quickly the function grows. It's not precise, but the reason that you can do that is because like they're all going to cancel out in the end anyway, right? We're going to divide by h and then take the limit as h goes to 0. Yep. Oh yeah, I should put the minus 1 here because it matters. Right. This is just the replacement. This is called linearization, right? This is a standard move in a lot of fields, right? To replace something with its linearization. So if you are uncomfortable with thinking about this as higher order terms, you can actually put the h squared over 2 factorial and h to the third over 3 factorial, right? It's the same argument. Because what happens is the 1 kills the 1, and then this turns into a limit as h goes to 0 of, well, h divided by h is 1, and if I have things that act like h squared and I divide them by h, they act like h. And that limit is 1. Oh, there's an e to the z running around in here too. So this is 1 e to the z. So in this particular case, taking the difference quotient got us e to the z, and also taking the derivative of the power series got us e to the z. So here, at least, the difference quotient and the term-by-term derivative of the power series matched each other. So the question is, why should this be true for a general function? For a general function, I don't have this easy move where I've got this really nice power series I can use, right? I might just have a general power series with coefficients in it, and some radius of convergence, not the nicest possible function that exists. I mean, it really is. Okay. So that brings us to the motivation for what we want to do today, which is we are going to prove the following theorem. So we are going to prove that f is analytic implies that f is holomorphic. We're going to say a little bit more than that because we're going to be able to talk about domains where that's true. But let's remind ourselves what the words mean before we start here. So an analytic function, f is analytic. Remember, these are the two most important words of the entire field, analytic and holomorphic. So you should be able to reproduce the definitions. F is analytic on some disk of radius r centered at some point A if f of z has a power series expansion. It converges absolutely on z minus a is less than r. So an analytic function is a function with a power series that convert, and I should be, like, one thing I missed here, r has to be positive. There is some disk on which the function has a convergent power series. So an analytic function is a function that has a convergent power series on some open set. Yep.
Maybe I'm just totally misremembering this, but didn't before you say converges uniformly?
Uniformly on a smaller disk inside this one. So
Oh, okay.
yeah, so it's uniformly and absolutely on any disk where z minus a is less than r, which is less than r. So as long as you stay away from the boundary, it's uniform convergence. That actually shows up in the theory of Fourier series as well. Okay, what does it mean for f to be holomorphic? F is holomorphic on, let's say the same set, the disk of radius r centered at A, if f is differentiable at all z contained inside that disk. And by differentiable, what we mean is that the limit as h goes to 0 of f of z plus h minus f of z over h exists. Okay? So analytic means you got a convergent power series. Holomorphic means that you're once differentiable. One of the things we're going to pick up in this theorem is that once differentiable implies infinitely differentiable. So the name of the theorem that we're going to prove here, Johnston calls it the infinite differentiability theorem. Yep.
In that context, what does like uniformly mean? Like all of the same point or number?
So uniform convergence, I should be careful here. So what uniform convergence means is that the limiting function has all the properties that the sequence, that the power series does. So if you have a power series and you think about adding term by term by term onto the end, that sequence of functions converges with tight control over the entire domain of the function to whatever the limiting function is. If you've taken 412, it's the difference between pointwise convergence and uniform convergence. Uniform convergence is stronger. It means that there's complete control over convergence everywhere at the same time. We won't need that here, but it's a good question. Okay. So, again, fundamental definitions to the class. All right, so let's prove the theorem. So let's suppose that f of z is equal to, we're going to make an assumption here that's going to make all the computations slightly easier, but it's a without loss of generality thing. So n equals 0 to infinity of cn z to the n. So we're going to let the center of the function be at 0. Doesn't change the argument, but I don't have to write minus a all over the place. So we're going to suppose that f of z has a power series representation for some radius bigger than 0. How would we show that the difference quotient and the derivative of the power series, what should the derivative of the power series be? What do we really want it to be? If I took a term-by-term derivative of this power series, what do I get? Like what is the goal statement here? That f prime of z is equal to what? Yeah, n equals 1 to infinity of n cn z to the n minus 1. I take the derivative of each term on the inside and put it together. If this thing is going to be if the derivative is going to have a power series, it better be this. That's what we want to show. But of course, what's f prime equal to? That also has a definition. F prime is equal to the limit as h goes to 0 of f of z plus h minus f of z over h. And what we want to do is we're going to show that this difference quotient is equal to this power series. That's what we really like to be true. The derivative will have the power series we want it to if this difference quotient, which is how we compute the derivative, and this power series are equal to each other for all the z's on which both of these operations are defined. All right? How am I going to do that? A lot of you guys are taking analysis. What am I going to do? Well, this is not actually an epsilon proof. It's a good impulse, but we can actually get away with not using epsilons, but the idea is going to be the same. How do I know two things are equal to each other and when one side is a limit? If the difference between them gets small, right? If you let h go to 0, and whatever this number is and this number get really close to each other, then they must be the same number, right? That's what it means to be a limit. So we're going to look at this. We're going to look at f of z plus h minus f of z over h minus this power series. N, Cn, z to the n minus 1. And the hope is that that thing is going to get small. If I can show that that difference gets small as h goes to 0, then I'll have shown that those two quantities are equal to each other. Oh, man. What kind of nightmare math is this going to be? Okay, well, we only have one move here, which is the same move we use in the exponential, which is, you actually suggested this earlier, I think. Put the power series in place of f. We only know one thing about f, which is that it has a power series. So let's put it in. Oh, don't groan yet. Just wait. Save your groans. So we're going to write this as the sum of n is 0 to infinity. See, this is going to be the hardest thing we do for a couple weeks, right? So we should spend some time appreciating it. Minus the sum from n equals 0 to infinity of Cn z to the n all over h minus the sum from n is equal to 1 to infinity of n Cn z to the n minus 1. Oh man, this is starting to look bad. Okay, so what's the strategy going to be? Yep. I'm going to combine everything together into one sum, and I'm going to try to show that that sum gets small. Okay? Ugh. Okay. So if you do that combination, you get this. The sum from n equals, hold on, I actually might need to, I have a lot of this in my head, but I don't quite have all of it. Let me turn to page 3 here. So that gets you, n is equal to, okay. Okay, so I'm going to write something down. I mean, so like, what's the first thing that's going to happen here, right? So the idea is that I have this series right here where I have n, these start at 0 and this one starts at 1, right? But the very first thing I'm going to do is I'm going to throw these first terms away. Why am I allowed to do that? Because if I put 0 in here, I get C0. And then if I put 0 over here, I get C0. And C0 minus C0 is 0. So I might as well just restart these terms. I don't change anything by starting these sums at 1. Right? The total doesn't change. So I'm going to rewrite this as the sum from n equals 1 to infinity. Everything has a Cn inside of it. And then what's left? Z plus h to the n. I should be careful with h's here. Minus z to the n over h minus n z to the n minus 1. There's no absolute values yet. Okay, so what did I do? I pulled all of these things into one sum, and the justification for that was these can be combined into one sum because they have the same index and they have the same powers, right? Then you can drop the n equals 0 term here to get n equals 1, because C0 minus C0 is 0, and then you can just sort of, everything has a Cn inside of it. You can combine this sum with those and jam it all together as this algebraic monster. So this is just algebra. I've done nothing complicated at this point, just algebra. It might look complicated, but. Okay, so now what? Well, this is kind of annoying. So what I'm going to do, notice that the problem here is that this grows with the size of n, right? The number of terms of this thing, as n gets larger, this gets more and more and more terms inside of it. So I'm going to use the binomial theorem to expand this into a sum. What does the binomial theorem say? The binomial theorem says that if you have the sum from n equals, no, sorry, not what it said. So the binomial theorem, this is good because it has all kinds of math inside of it. So the binomial theorem says that z plus h to the n is equal to the sum from n equals 0, sorry, k equals 0 to n of n choose k, z to the n minus k, h to the k. So you learned this in Calculus 2. Whether or not you remember it, you did. Right. The idea, so these are combinations. There's a formula for this. If you don't remember, I think n choose k is equal to n factorial over k factorial times n minus k factorial. It's the combinations. Also called the binomial coefficients, also called Pascal's triangle. Right? But basically that's a theorem that lets you replace an expansion like this with a sum. So what we're going to do is we're going to take this and we're going to replace it with that. The next move. So the next thing is that we want to show that this sum acts in a way that we want it to. So I'm just going to isolate this term for right now. We're going to keep this on the board, and we're going to come back after we've done some estimating and replace this with what it's equal to. Okay, so we're just going to isolate this term and see what we can say about it. Okay, so that thing, z plus h to the n, h, minus z to the n over h, minus n z to the n minus 1, it's going to be equal to the sum from k equals 0 to n of n choose k, z to the n minus k, h to the k, minus z to the n over h, minus n z to the n minus 1. You might think, okay, what have I actually gained by doing this? Well, notice that this is going to eat the z to the n. Because the first term of this, if you actually wrote down what this is equal to, this is equal to z to the n plus n choose 1 z to the n minus 1 h plus n choose 2 z to the n minus 2 h squared, and so on, right? So the very first term here, n choose 1 is n. So the z to the n is going to get eaten because there's a z to the n right there. And also, magically, this is going to get eaten too eventually because the h's are going to go up here and be canceled, and then this will also cancel out. So algebraically, the next step is to notice that z to the n is the k0 term of this series. And so we get the sum from k equals 1 to n of n choose k, z to the n minus k, h to the k over h minus nz to the n minus 1. So the trick here is we're getting rid of all these extra bits to get something I can actually control. So all these extra subtractions are being eaten up. So the z to the n subtracted off this, and that's when we dropped to the first index. But hey, now look, every single term has an h inside of it. Because k equals 1 has an h, and k equals 2 has an h, and k equals 3 has an h. I'm actually just allowed to divide all of this by h. And that gets me the sum from k equals 1 to n of n choose k, z to the n minus k, h to the k minus 1, minus n z to the n minus 1. And guess what the k equals 1 term of this series is? It's that dude. So one more algebra step gets you the sum from k equals 2 to n of n choose k, z to the n minus k, h to the k minus 1. So this dude right here is where we're at right now. All of this is the same as that. Now, we're not done, but that's where we are in the process of doing this estimate, right? So when you're doing estimates, it's all about reducing to something useful. If your question is, how on earth did anybody ever come up with this? The answer is 200, 300 years of mathematicians working on a problem ends up in arguments that look like this one, where everything is just so. Okay, so what we're going to be interested in doing is a convergence test. And so we're actually going to be looking at absolute values of this thing. So we're going to be using the root test or the ratio test. And so we want to take absolute values of this, because those are tests for absolute convergence. Ultimately, the root test is going to be invoked here, which is going to tell us something about what the CNs do. So let's look at what this would do underneath the action of an absolute value. That's actually how mathematicians work, right? These are all still complex numbers, and that sucks. Let's replace them with real numbers, which are nice. I mean, complex numbers don't suck, but they suck to work with in series. Okay, so how do we do that? So the absolute value of the sum from k, I'm going to make a move and you tell me why it's true. And choose k. In fact, there's only one move in analysis. I don't know how many people in this class have had me before. A lot of you. So an analyst only have one move. We have one tool. It's a hammer. Yeah, so you know this old saying about if all you have is a hammer, every problem looks like a nail? Analysts can do one thing. Triangle inequality. That's what we have. There's nothing else. We have the triangle inequality. And so our entire lives are manipulating things so we can apply the triangle inequality. You might have got that impression if you took 412, and it's true. So this is less than or equal to the sum of the absolute values. And choose, those are always positive. Absolute z, n minus k, absolute h, k minus 1. Why do that? Because now these are real numbers that potentially I could work with a radius, or I could work with a root test if I needed to. So I've switched my complex numbers out, and I'm studying these guys instead. Yep?
Why can't you just take the limit as h approaches 0 in the previous step and follow
Because I don't know what converges. What test are you going to use to argue that this converges? These are not, one, this doesn't run to infinity, this only goes to n, so it must converge. So certainly the limit is 0, but remember, this sum is piled up inside of a big sum. So it's right now it's a sum of, this thing is just this one term. And as the n's get larger, this gets bigger and bigger and bigger. So how do I know that the size of the polynomials that are growing in here is not overwhelming the fact that the h is going to 0? That's actually the crux of the entire problem. Yes, h is going to 0, but h is going to 0, but these polynomials are enormous, right? And because the power of the polynomials keeps going higher, it's like you have this boiling polynomial that just grows enormously. So all of this is necessary because we don't actually know what the interaction is between the growth of the polynomial, which is doing one thing, and then the shrinking of the h, which is doing something else. All right?
Yeah.
Okay. Okay, now I'm going to make an absurd, I'm going to make an estimate. Okay, now, maybe, I hope you guys believe me. I'm going to make a statement here. This thing, we originally assumed that f converged. The series for f converged for an absolute value of z less than r. We made that assertion, right? We had a power series that converged for a positive radius of convergence, and it converged for all z's contained in this disk. That means there's room. For any fixed value of z, there's room between the modulus of z and the radius r, right? Okay, what is h doing? What are we ultimately going to do with h? So h could be as small as I want. I could just make h whatever size I feel like, because h is going to go to 0. So I'm going to assume that h is small enough, that the magnitude of h is small enough, so that the modulus of z plus twice the modulus of h is less than r. That seems a reasonable thing to say. Since h is going to 0, I should be able to make h small enough so that it fits between the modulus of z and this radius r, because there's space there. That's a 2h. Did I say 3 somewhere? Yeah, no, it's a 2.
I think it's a z or 2.
Yeah, this is a z, this is a 2h. Modulus of z and the radius have room between them because z has to be in the disk of convergence. So there's some space between, so I just make h small enough so that it fits in the gap. Oh, but I'm actually going to reconstruct this into an estimate that I'm going to use. This is a just so construction, right? The 2 here is because I want to write this. If I solve this for mod h, I get this. The modulus of h is less than r minus the modulus of z over 2.
I mean, you could like assume it's small enough that it's anything, right, in front of that.
What do you mean? Oh, yeah, I can pick any. So in these arguments, part of the reason to show you guys this is to show you how much like finagling is going on behind the scenes, right? Somebody figured out that the optimal way to do this argument was to put a 2 right here, but you could put any number you wanted because h could be as small as you want. It's going to turn out to be convenient from a geometric perspective to think about this 2 being right here. Okay. Okay, now why would I do that? Because this actually is going to be a way to get the h's out of the problem eventually, right? Ultimately, what I want to do here is that there's going to be a whole bunch of h's I want to get rid of. Okay. Back over here. Okay. Now, an appropriate question at this point is, what the hell does the h in that estimate have to do with what we're trying to compute? After all, here's where we are. I know all this stuff is equal to that. What is this doing? Like, why is that in there besides driving me crazy? So, let's do this. So, I would hope that it's reasonable for me to do this. From 2 to infinity of n choose k mod z. You guys catch me if I write something down. What did I do? Oh, yep. 2 to n. Yeah, I mean, dude, these are hard to do, right? It's this is hard. This is exhausting to do. Okay, so now what we're going to do is we're going to take this and we're going to split it into 2 convenient pieces. 2 to n choose k, modulus of z to the n minus k, and then what I'm going to do is I'm going to sort this into a modulus of h and a modulus of h to the k minus 2. Okay, the reason I'm doing this is because ultimately what's going to happen is I'm going to sort this back into a binomial expansion, right? I'm going to go the other direction with it. It looks artificial, but I promise we did that for a reason. Okay, now what I'm going to do is I'm going to take all of this stuff and I'm going to replace it with this estimate. So this is less than or equal to, not even less, that's a strict. This is less than the sum from k equals 2 to n of n choose k, modulus of z to the n minus k, modulus of h, because why not keep an h in the problem? Something has to go to 0 eventually. And then this h to the k minus 2 is going to become r minus the modulus of z divided by 2 to the k minus 2. For any fixed z, this is just some number. That's why we chose it, right? This is just some way to get the h's out of this part. I put a less than here because I'm replacing h with something that is larger than h. So if I'm adding a series of positive, why do we use absolute values? This is a series of positive terms. If I replace a positive number with a larger positive number, then the series gets larger. All right, now I'm going to factor out an h and also the negative 2 of these. And then we're almost ready for my favorite move in this entire argument, which is ridiculous. Okay, so I'm going to do is I'm going to take out the negative 2 of these that are inside here to leave the k behind. I get this sum. K is 2 to n of n choose k, modulus of z to the n minus k, modulus r minus modulus of z over 2 to the k. Does anybody see the suspicious thing that happened here? If I covered up that k equals 2, that looks like a binomial expansion. I have n minus k and k in the binomial coefficients. So if this started at 0, I could just refactor that. But I'm working in modulus. So adding 2 more terms to a series just makes it get bigger. So this is less than, so what I'm going to do is I'm going to put the k equals 1 and k equals 0 terms back into this. It's a series of positive numbers, I'm allowed to do that. So this is less than modulus of h, and r minus modulus z over 2 to the minus 2. And now a sum from k equals 0 to n of n choose k modulus of z to the n minus k r minus modulus of z over 2 to the k. So the move here was this. This is a series of positive terms. If I take 2 more positive terms and throw on, it's not equal, but it's less than, because I just added 2 more positive numbers to the pile. And now the ridiculous move where this is a binomial expansion. And it's a binomial expansion of this. R minus modulus of z squared. Okay, what happens here? This is z plus r minus modulus of z over 2 to the n. So I unbinomialed it. Is that okay? Yep.
Did you drop the -2 on the?
Did I lose a 2 somewhere?
Z piece? The right out in front of the sum, there was an
Yeah.
equal to the exponent.
Negative two exponent.
Oh, yeah. We did not drop that. That's just me dropping it. So the point here is that for a fixed, so the question, okay, again, let's like take stock here for a second because this is just a lot of math, right? The idea is that what we've done is we took a series that had, it grew in n. As n got larger and larger, this polynomial just boiled out with h's all over the place, right? This is hard to understand. And what we're going to do is we're going to replace this with a term that only has a single h inside of it. And now this thing does boil with n, but there's no h's here. There's no h's anymore. And this is actually mod z, I forgot. Mod z times this thing. Okay, so now what we're going to do is we're going to take all of this stuff and we're going to put it right there. And we're going to hit it with the root test. Before we do that, we should ask ourselves what we know about this number right here. What do I know about that number? Where does it live? Modulus of z plus r minus modulus of z over 2. You think maybe that number, it would be really great if that number was inside the radius of convergence of the power series, because then there would be Cn times numbers that were inside the radius of convergence of the power series, and the whole thing would converge, right? It's like literally by construction, it's in the, yeah, that the whole point of it is that we forced it to be in there. And the idea is that r plus the modulus of z over 2 is less than r, right? Minus. By construction, that statement is true. This is why we did this, was to force this to be true. So this number right here, all of this number, this is inside the radius of convergence. So if you want, you could think about it as like an or something like that. It doesn't, at this point, for a fixed z, it does not matter. This is just a number. Okay, so now we're at the home stretch here. Okay. So let's make the final substitution. So we're going to take this power series. Yep.
I get that the number we constructed is inside the radius of convergence, and so is modulus of z, but how do we be sure that the two of them added?
I mean, if you actually take this and add it together, you get an expression that's less than r. You can actually test the inequality,
Okay.
right? I mean, this, yeah, this you can actually test this. You can put this less than r and prove that that's true. Okay, so what was I doing with that? That's, yeah, I mean, that the whole point of the original estimate here was it forces that to be the case. That's actually why we chose the numbers that we did. Okay, so in the final state of being, we have this. we have the absolute value of f of z plus h minus f of z over h minus the sum of n cn z to the n minus 1. We did a whole lot of grinding on this. That's an h. This is n is 0 to infinity. And at the end of the day, what this boils down to is that this is equal to the absolute value of this thing. Sum from n equals 1 to infinity of cn z plus h to the n minus z to the n over h minus n z to the n minus 1. And then what our estimate did, this estimate right here lets us do this move. Did I miss something?
It's less than or equal to, right? Not equal to.
Yeah. Well, no, these are actually equal because this was equal. We haven't done it less than or equal to yet. This computation right here was directly from this computation. The estimate happens now. I haven't done anything yet.
Oh, yeah, sorry.
This is
I
literally
thought-
just like all I do. I know there's a lot of steps here. Yeah, there's no less than yet. Now we're going to do the less than because we're going to replace this thing with this. And that's going to get us, that's less than the sum from n equals 1 to infinity of cn. And then we have, we can factor out. Should we do the factoring? H modulus of z minus r over 2 r minus mod z. So minus 2, and then a sum of the absolute value of the cn's times the absolute value of r plus modulus of z over 2 to the n. If you add this, if you do this computation, you get that. Right? Form a common denominator and add them together, you get this. So this is that. What do I know about the modulus of z? It's less than r. So r plus something less than r divided by 2 is less than r. So this number is within the radius of convergence of the power series. Okay, so we're ready. That's just some number. Does it contribute to any limits? No. This is a power series. Why does it converge? That number is smaller than r, and the absolute value of the coefficients, that's the same as the coefficients from the first power series, which converged this converges by the root test. We know this converges, yep.
That second term in the sum, is that in the modulus or is that in brackets?
It doesn't, we applied modulus here, so it's in modulus, but it doesn't matter because this is a real number and it's positive.
Right, okay.
So we can put it in brackets, we can put it in modulus, it's positive, it doesn't matter. But the idea is, this is a number. This thing converges because the coefficients have to converge by the root test. And that number right there is within the radius of convergence for those particular set of coefficients. That's what the original assumption was about. F converged when the modulus of z is less than r, but by the root test, that means the coefficients are what dictate what the series does. So the conclusion is, this thing, so here's a number, and this thing converges for any z with modulus less than r. So what happens when we take the limit as h goes to 0?
0.
Yeah. That's it.
Great.
Put a limit as h goes to 0 right here. All of this is just some number. Oh, look, there's a modulus of h stuck on front. So if I take a limit as h goes to 0, this is just nothing. So the limit of the differences goes to nothing because this enormous, ridiculous computation turns out to have a single remaining h inside of it in the numerator. Okay, so what do we get out of this absurd? I will post the notes on this if you guys didn't catch everything here. So are you responsible for this argument? No. Should you understand all the pieces that we made inside of it? Yes. We didn't do any, notice, there was no move we did in here that wasn't a calculus move. Every single move in this argument was a calculus move. Yep.
So we showed something greater than the original series converges to 0.
We showed that the modulus of something greater than the original series converged, right? So what did we show? We showed that the size of the difference between the difference quotient and the series went to 0. So if the size of the difference between two things goes to 0, then the difference between two things goes to 0. The fact that that difference goes to 0, the distance between these two objects goes to nothing, means they are the same object.
And there's no like qualm with the fact that you're using inequality to show that?
No, because that's actually, it's precisely, the inequality actually is in some sense easier to work with. But no, if I say f minus g, the distance between f and g go to 0, then f is equal to g, right? I mean, okay, those of you that know about like Lebesgue measure and stuff like that, we just forget that, right? We're not, this is complex analysis, everything's analytic. Okay. So all of the whole point of the computation was to produce this estimate that turned our original series into a series that was stuff that was a number times one copy of h going to 0. And that means that goes to 0, which means that difference is always 0 for all z that have the proper radius of convergence. And so we get two conclusions out of this, two really good conclusions. The first is, have we proved that the difference quotient and our desired power series for the derivative are equal to each other? And the answer is yes, that is exactly what this argument did, right? This argument proves that if f is equal to the sum from n equals 0 to infinity of cn z minus a to the n, then, oh, and for some radius r greater than 0, then f prime of z is equal to the sum from n equals 1 to infinity of n cn z to the n minus 1. So the first thing we proved is that the formula works. And by f prime of z, I mean the limit is h goes to 0 of f of z plus h minus f of z over h. The way that we find the derivative and the form we really want its power series to hold are equal to each other. But we get more, because what that means is the derivative is analytic. So I could take its derivative, because analytic functions have derivatives. So what we proved was if f is analytic, the derivative is equal to this power series, but a function having a power series means it's analytic. So f analytic implies f differentiable, and as a bonus, f prime is analytic. We proved it's differentiable because we proved that this difference quotient approaches something. And we proved it's analytic because we proved that the thing it approaches is a power series. So what's to stop us from turning the crank and doing the same argument on f prime? The answer is nothing. I could just as well say, well, if f prime is analytic, apply the theorem again. And so f prime is analytic implies that f double prime is analytic. And f double prime analytic implies f triple prime analytic. So this is why this is called the infinite differentiability theorem. We've also shown, as part of this, like the upshot of this theorem is, if f is analytic, so are all of its derivatives. And f is infinitely differentiable. So I can take as many derivatives as I want, and they all have power series. So this is a remarkably strong theorem. Yep?
Do we have to ensure that the limit, the difference quotient, exists before?
No, because no, actually, because we didn't know going in that this difference quotient was going to converge to anything, right? But what we showed is that what we've done here, really in secret, was assert that this was the L that the difference quotient converged to.
Right.
So we've proved that the difference quotient converges to L, and then that limit L is a thing that we call f prime of z for a given z. So we've proved that the difference quotient converges, right? Showing that it has a limit is the same as saying that f is differentiable. And since it works for all z inside the radius of convergence, that says that f is holomorphic on that. Or that f prime is holomorphic there. So that's pretty awesome because f is analytic, so all of its derivatives, all the derivatives exist. Oh, also, yeah, f is holomorphic. but it's better than holomorphic. It's infinitely differentiable. So complex functions are amazing, right? The fact that you can do this with calculus is pretty ridiculous, but complex functions have tons of structure. Assuming that a complex function has a power series is enough to guarantee all the derivatives also have power series, and the function is infinitely differentiable on an open set. So next time, we'll go back to normal and not wild again. So we'll step away from highly technical proofs. I'll post my notes on this. We're going to go back to talking about how we deal with branch cuts, how we deal with inverse functions, and it's going to be more computational again. So thanks for your attention. Those of you that want codes,